Hey, what's up, tutor? Dude, I'm totally struggling with like what in the world is normal force, man? I don't understand that. Just can you explain it to me? Normal force and potential energy and kinetic energy. What is all of that, man? Can you help me, please? Well, I do suppose I could help you with this since I'm Fall Academy. Let's start with how to prove that if you release a roller coaster, at what height would you have to release it just for it to barely go, just to for it to go around the loop to loop, just like go around it. I will show you this proof, and I will show you, and in this proof, there's gonna be uh, there's gonna be centripetal acceleration, circular motion, and potential energy, normal force, all of that, man. And I will show you this right now. Okay? So here I go. Let me show you this. Let me show you this. Let me show you this. Let me show you. So let's say we have some type of roller coaster, right? Goes around like that. Should I use black? Yes, I think I should use black. Show you this, Say you have a roller coaster. Some type of loop-de-loop. Say this is a perfect circle. I mean, I kind of drew it bad, but say the radius is R, right? And let's say this height right there is like, we don't know it. Let's just label this H, right? Let's just label that H. Say we have a block. It's just the block is the roller coaster, okay? And of course, if it's circle, if it's not a sphere, because if it is, then we have to consider the rotational kinetic energy at here. I mean, and we don't want to mess with that. So, how do we prove that this height has to be exactly 5r over 2? This has to be 5 times the radius, this height right there. This height right here has to be 5r divided by 2 for this block to go completely around the circle without falling down when it reaches this point. How do we prove that? First, let's examine circular motion. What do we know about circular motion? We know first, let's define centripetal force. What's centripetal force? Is what's making this thing go around the circle, right? And then we know centripetal force is just like the net force, basically the net force for an object going around a circle. And we know at this point the normal force is pointing down, because what is the normal force? First, we need to define it. If you have a block just sitting, like standing on a surface, like you have a block sitting on a surface, basically. Newton's third law: the block reacts. I mean, the block puts some force on the surface. Just label that there so there's no confusion. And the surface puts some force on the block, and that's this. And we define that as the normal force, basically, right? Right. So basically, if this block was to be here, the normal force will be pointing. This surface will push on the block this way, and that will be the normal force, basically. And gravity will be pushing down on the block too, right? So we could write this as sigma F, which is the same as the centripetal force, because we don't want to get that confused, right? Same as the centripetal force, which is the same as the force of gravity plus the normal force, because since they're pointing in the same direction. And we know the F net is the same as mass times acceleration, right? Right? And we know the acceleration of an object, for if it's going around a circle, is the same as v squared over r. So we could write mass times acceleration as mv squared over r, right? And this equals the force due to gravity, which is mg plus the normal force. Now what are we trying to prove? We're trying to prove and then after we examine this using this equation, we will see why the centripetal acceleration would have to be greater than or equal to the gravitational energy. So basically, the normal force must be zero when this block is at when it's at this position. Why must the normal force be zero? Because I will just show you this right now. I'm going to show you right now. Just wait. Basically, if you have a block sitting on a surface, the normal force points up, right? Because it's the reaction of the surface and the block, right? But if the block is barely touching the surface, like barely even touching it, the normal force must be zero, because the block is not pushing down on the surface, because it's barely touching it. So the normal force is zero. If there's someone holding it, right? Never mind my drawings, but that's a hand, and they're holding it, and then the block is barely touching the surface. That means the normal force is zero, because the block is not pushing down on it. So basically, if the height is barely long enough for the block to go completely around the loop-de-loop, the normal force at this point will be zero. I hope that's clear. Let's just erase this, and just erase this. So now we know what the normal force is. It's basically a reaction of, but what normal force is basically Newton's third law of examining it. Normal force is basically Newton's third law. Just want to make it simple, So if we know that the normal force is zero, that means the centripetal force F would have to equal. That means the centripetal force, right, would equal only mg. And we know, and this sigma F, which is centripetal force, is the same as mv squared r, since we've already proved that, right? The centripetal force will already equal mv squared r, the sigma Fy, because it's a centripetal force, and then this must be equal to or greater. This should be equal to or greater, right? This centripetal force must be equal to or greater than the force due to gravity for it to go completely around the circle. So having this, we could just cancel the masses out, and we could get that v squared divided by r must be greater than or equal to the gravity, acceleration due to gravity. So since this block is barely just going around this loop-de-loop, we could just say that it's equal to, and then use equations for that. We could just say that it's equal to for right now, since it barely just goes around this. It just barely goes around the loop-de-loop. So let's just erase this. So we already seen that. So now we could get some work. We know that v squared, the velocity at this point is What should we label this velocity? What should we label it? Okay, let's just make this called, let's call this A, so we can label this velocity, what this velocity would be. Let's label this B, let's label this C at that point, right? So we know that the velocity at C, let's just label it VC, over this radius must equal the acceleration due to gravity. So you just do proportions and stuff, and then you figure that VC squared, let's leave it in terms of VC squared, must equal G times R. VC squared must equal G times R. Let's just put that here, and we're trying to prove that this height, right, this height here must equal this. So we could erase that because we're gonna get it anyways. So, and then let's just put that VC squared must equal GR. Must equal GR. Everybody get that? Just put it there, and then we use. So now let's define what potential energy is, and then so we need to know what type of energy would the block have at point A. It's gonna have potential energy. Basically, you could define potential energy as like its potential to convert into other types of energy. Basically, kinetic energy is the energy of moving of a moving object, and potential energy is basically the potential of an object to convert to other forms of energy. You could show it like conceptually as basically you have a block connected to a spring. As you exert force on the spring, and then as the displacement of the spring rises, as you push up on the block, the spring will basically increase, and then if you release it, it will have more potential to go down. Basically, the less you put the block up, the less the block would want to go back down, and the more you push it up, the more it's gonna go down. Basically, the more kinetic energy it's gonna have, the higher velocity it's gonna have when it hits the surface. So that's basically what potential energy is: the potential for it to convert to other types of energy.